Welcome to my new series. Let's read together. We'll read STEM books for noobs. We'll start with the book Love and Math, The Heart of Hidden Reality by Edward Frenkel. We see Nassim Nicholas Taleb's commendation at the bottom. He's also written another famous book, Fooled by Randomness, which highlights the role of chance. Why this book? Let me start with the description. So he is Edward Frenkel. He got an Euler Book Prize in 2015 for this book, Love and Math. That book, the prize is for an outstanding book in mathematics that is likely to improve the public view of the field. So it's essentially for us. There is a secret world out there, a hidden parallel universe of beauty and elegance, intricately intertwined with ours. It's the world of mathematics, and it's invisible to most of us. This book is an invitation to discover this world. Consider this paradox. On the one hand, mathematics is woven in the very fabric of our daily lives. Every time we make an online purchase, send a text message, do a search on the internet, or use a GPS device, mathematical formulas and algorithms are at play. On the other hand, most people are daunted by math. Like us. It has become, in the words of poet Hans Magnus Enzensberger, a blind spot in our culture, alien territory, in which only the elite, the initiated few, have managed to entrench themselves. It's rare, he says, that we encounter a person who asserts vehemently that the mere thought of reading a novel or looking at a picture or seeing a movie causes him insufferable torment. But sensible, educated people often say, with a remarkable blend of defiance and pride, that math is pure torture or a nightmare that turns them off. Well, we can't mistake them. If we see equations like these and graphs like these, and if we try to read this, naturally this is enough for any person who is interested to feel discouraged. So let's continue. How is this anomaly possible? I see two main reasons. First, mathematics is more abstract than other subjects, hence not as accessible. Second, what we study in school is only a tiny part of math, much of it established more than a millennium ago. Mathematics has advanced tremendously since then, but the treasures of modern math have been kept hidden from us, hidden from most of us. Mathematics is more abstract than other subjects. What does abstract mean? Here we see an image of a man pushing a car. This is what physics treats it as. You get a normal reaction, and applied force, friction force, and weight. This is the totally mathematical abstraction. We move from here to here to here to here. More and more abstract. We simplify it. We focus here, we have the whole picture. Here we focus on the directions. Here we focus only on the calculations. This is what makes maths more abstract and pushes and keeps it away from ordinary people like us. What if at school you had to make an art class in which you were only taught how to paint a fence? What if you were never shown the paintings of Leonardo da Vinci and Picasso? Would that make you appreciate art? Let us continue. You would probably say something like this: learning art at school was a waste of my time. If I ever need to have my fence painted, I'll just hire people to do this for me. Of course, this sounds ridiculous, but this is how math is taught. And so in the eyes of most of us, it becomes the equivalent of watching paint dry. While the paintings of the great masters are readily available, the math of the great masters is locked away. The math of the great masters is locked away. So if we search for the proof of Fermat's last theorem, how many results actually show the website? So let us continue. However, it's not just the aesthetic beauty of math that's captivating. As Galileo famous said, the laws of nature are written in the language of mathematics. Math is a way to describe reality and figure out how the world works, a universal language that has become the gold standard of truth. In our world, increasingly driven by science and technology, mathematics is becoming even more the source of power, wealth, and progress. Hence, those who are fluent in this new language will be on the cutting edge of progress. How true is this statement? If you understand math, can you really control the world? Let us see some of the world leaders. US President Donald Trump, who is famous for his mistakes, but the previous president, Biden, had on his council of advisors the Mozart of maths, Terence Tao. This is a list of UK Prime Ministers. The second last was Rishi Sunak, an investment banker. Tech giants like Apple, Nvidia, Microsoft, Google employ people from a strong maths background, like Geoffrey Hinton, who pioneered the neural networks through the Boltzmann machine. This is the machine that some people think could become conscious and destroy the world. And most recently, we have had OpenAI, O3, which has taken the tech world by storm. It has scored the highest on the RKGI benchmark, the benchmark that keeps computers from completely replacing us. One of the common misconceptions about mathematics is that it can only be used as a toolkit. A biologist, say, would do some field work, collect data, and then try to build a mathematical model fitting these data, perhaps with some help from a mathematician. While this is an important mode of operation, math offers us a lot more. It enables us to make groundbreaking paradigm-shifting leaps that we couldn't make otherwise. For example, Albert Einstein was not trying to fit any data into equations when he understood that gravity causes our space to curve. In fact, there was no such data. Wow. There was no such data. No one could even imagine at the time that our space is curved. Everyone knew that our world was flat, but Einstein understood that this was the only way to generalize his special relativity theory to non-inertial systems, coupled with his insight that gravity and acceleration have the same effect. How do gravity and acceleration have the same effect?
3, 2, 1, go.
When the car accelerates, the person gets pushed backward into the seat as he accelerates forward, just as we get pushed into the ground because of gravity. Thus the direction is different, but the effect is the same. Even the magnitudes are comparable. 0 to 60 in 2.23 seconds is 12 meter per second square, which is close to 9.8 meter per second square, the value of gravity or acceleration due to gravitation. This no one could even imagine at the time that a space is curved. While Einstein says that our space is curved, we don't need curved space to explain the equations.
Yes, you already knew that a sphere isn't flat, but the point is that you don't need to be able to look at the sphere from the outside. You can infer its curvature entirely from measurements on the sphere. When it comes to the curvature of space and time, it's the same thing. We say that curved because of properties that we measure entirely on the inside. The things we measure are observable, such as the redshift of light, or the travel time, or the paths on which bodies move, and so on. You could ask now, well, if those are all things we measure on the inside, what sense does it even make to call this curvature? Couldn't we just say that space-time is flat, just that these observables have difficult relations that are mediated by some sort of field? Indeed, this is a valid interpretation of the maths, that you refuse to give this a geometric interpretation and instead just say gravity is determined by some sort of complicated field. This is why Steven Weinberg, in his book on general relativity, famously refused to use a geometric interpretation. You don't need it.
Let's continue. Let's ignore that Albert Einstein said something wrong. No one could even imagine at the time that our space is curved. Everyone knew that our world was flat. But Einstein understood that this was the only way to generalize his special relativity theory to to non-inertial systems, coupled with his insight that gravity and acceleration have the same effect. This was a high-level intellectual exercise within the realm of math, one in which Einstein relied on the work of a mathematician, Bernard Riemann, completed 50 years earlier. Wow. The human brain is wired in such a way that we simply cannot imagine curved spaces of dimension greater than 2. We can only access them through mathematics. And guess what? Einstein was right. Our universe is curved, and furthermore, it's expanding. That's the power of mathematics I'm talking about. Many examples like this may be found, and not only in physics but in other areas of science. We will discuss some of them below. History shows that science and technology are transformed by mathematical ideas at an accelerated pace. Even mathematical theories that are initially viewed as abstract and esoteric later become indispensable for applications. Charles Darwin, whose work at first did not rely on math, later wrote in his autobiography, "I have deeply regretted that I did not proceed far enough, at least to understand something of the great leading principles of mathematics. For men thus endowed seem to have an extra sense. I take it as prescient advice to the next generations to capitalize on mathematics' immense potential." When I was growing up, I wasn't aware of the hidden world of mathematics. Like most people, I thought math was a stale, boring subject. Yeah, I agree. But I was lucky. In my last year of high school, I met a professional mathematician who opened the magical world of math to me. I learned that mathematics is full of infinite possibilities, as well as elegance and beauty, just like poetry, art, and music. I fell in love with math. Dear reader, with this book, I want to do for you what my teachers and mentors did for me. Unlock the power and beauty of mathematics and enable you to enter this magical world the way I did, even if you are the sort of person who has never used the words math and love in the same sentence. Mathematics will get under your skin just like it did under mine, and your worldview will never be the same. Mathematical knowledge is unlike any other knowledge. While our perception of the physical world can always be distorted, our perception of mathematical truths can't be. They are objective, persistent, necessary truths. A mathematical formula or theorem means the same thing to anyone, anywhere. No matter what gender, religion, or skin color, it will mean the same thing to anyone 1,000 years from now. And what's also amazing is that we own all of them. Wow. We own all of mathematics. Essentially, no one can patent maths. No one can patent a mathematical formula. It's ours to share. There is nothing in this world that is so deep and exquisite and yet so readily available. Wow. That such a reservoir of knowledge really exists is nearly unbelievable. It's too precious to be given away to the initiated few. It belongs to all of us. Yeah, I agree. One of the key functions of mathematics is the ordering of information. This is what distinguishes the brushstrokes of Van Gogh from a mere blob of paint. With the advent of 3D printing, the reality we are used to is undergoing a radical transformation. Everything is migrating from the sphere of physical objects to the sphere of information and data. We will soon be able to convert information into matter on demand by using 3D printers just as easily as we now convert a PDF file into a book or an MP3 file into a piece of music. While ChatGPT wasn't available at that time and Gen AI wasn't there, today we have it. We can create an MP3 file from a text prompt. The book was written in 2015. In this brave new world, the role of mathematics will become even more central as the way to organize and order information and as a means to facilitate the conversion of information into physical reality. In this book, I will describe one of the biggest ideas to come out of mathematics in the last 50 years, the Langlands program, considered by many as the grand unified theory of mathematics. It's a fascinating theory that weaves a web of tantalizing connections between mathematical fields that at first glance seem to be light years apart. Algebra, geometry, number theory, analysis, and quantum physics. If we think of those fields as continents in the hidden world of mathematics, then the Langlands program is the ultimate teleportation device, capable of getting us instantly from one of them to another and back. Launched in the late 1960s by Robert Langlands, the mathematician who currently occupies Albert Einstein's office at the Institute for Advanced Study in Princeton. The Langlands program had its roots in a groundbreaking mathematical theory of symmetry. Its foundations were laid 2 centuries ago by a French prodigy, just before he was killed in a duel at age 20. It was subsequently enriched by another stunning discovery, which not only led to the proof of Fermat's last theorem, but revolutionized the way we think about numbers and equations. Yet another penetrating insight was that mathematics has its own Rosetta Stone and is full of mysterious analogies and metaphors. What is a Rosetta Stone? The Rosetta Stone is a historic artifact that played a crucial role in understanding ancient Egyptian hieroglyphs. Discovered in July 1719 by French soldiers during Napoleon's invasion of Egypt, this granodiorite stele is inscribed with 3 different scripts: hieroglyphic, demotic, and ancient Greek. Okay, it's like a dictionary. Let's continue. Following these analogies as creeks in the enchanted land of math, the ideas of the Langlands program spilled into the realms of geometry and quantum physics, creating order and harmony out of seeming chaos. I want to tell you about all this to expose the sides of mathematics we rarely get to see. Inspiration, profound ideas, startling revelations. Mathematics is a way to break the barriers of the conventional, an expression of unbounded imagination in the search for truth. George Cantor, creator of the theory of infinity, wrote, "The essence of mathematics lies in its freedom." I agree. Even though you are wrong, you can write whatever you want. Mathematics teaches us to rigorously analyze reality, study the facts, follow them wherever they lead. It liberates us from dogmas and prejudice, nurtures the capacity for innovation. It thus provides tools that transcend the subject itself. These tools can be used for good and for ill, forcing us to reckon with math's real-world effects. For example, the global economic crisis was caused to a large extent by the widespread use of inadequate mathematical models in the financial markets. Most of the decision makers didn't fully understand these models due to their mathematical illiteracy, but were arrogantly using them anyway, driven by greed, until this practice almost wrecked the entire system. They were taking unfair advantage of the asymmetric access to information and hoping that no one could call their bluff because others weren't inclined to ask how these mathematical models worked either. Perhaps if more people understood how these models functioned, how the systems really worked, we wouldn't have been fooled for so long. There is a course on edX which is about the financial crisis. Let's continue. As another example, consider this. In 1996, a commission appointed by the US government gathered in secret and altered a formula for the consumer price index, the measure of inflation that determines the tax brackets, Social Security, Medicare, and other indexed payments. Tens of millions of Americans were affected, but there was little public discussion on the new formula and its consequences. And recently there was another attempt to exploit this arcane formula as a backdoor in the US economy. So this is the video I want to show you.
On Earth would they remove food and energy from inflation data. Food and energy are probably the 2 most important things required for the survival of any human. And believe it or not, the version without food and energy is actually the preferred measure of inflation that central banks like the Federal Reserve use to gauge inflation.
So that is how the Federal Reserve manipulates the CPI and shows us a rosy picture of itself. Far fewer of these sorts of backroom deals could be made in a mathematically literate society. Mathematics equals rigor plus intellectual integrity times reliance on facts. We should all have access to the mathematical knowledge and tools needed to protect us from arbitrary decisions made by the powerful few in an increasingly math-driven world. Where there is no mathematics, there is no freedom. Mathematics is as much part of our cultural heritage as art, literature, and music. As humans, we have a hunger to discover something new, reach new meaning, understand better the universe and our place in it. Alas, we can't discover a new continent like Columbus or be the first to set foot on the moon. But what if I told you that you don't have to sail across an ocean or fly into space to discover the wonders of the world? They are right here, intertwined with our present reality, in a sense within us. Mathematics directs the flow of the universe, lurks behind its shapes and curves, holds the reins of everything from tiny atoms to the biggest stars. This book is an invitation to this rich and dazzling world. I wrote it for readers without any background in mathematics. If you think that math is hard, that you won't get it, if you are terrified by math, but at the same time curious whether there is something there worth knowing, then this book is for you. There is a common fallacy that one has to study mathematics for years to appreciate it. Some even, I agree. Most of the math I had to study seemed pretty out of my grasp. Some even think that most people have an innate learning disability when it comes to math. I agree to an extent. I disagree. Most of us have heard of and have at least a rudimentary understanding of such concepts as the solar system, atoms and elementary particles, the double helix of DNA, and much more, without taking courses in physics and biology. And nobody is surprised that these sophisticated ideas are part of our culture, our collective consciousness. Likewise, everybody can grasp key mathematical concepts and ideas if they are explained in the right way. I agree. To do this, it is not necessary to study math for years. In many cases, we can cut right to the point and jump over tedious steps. Let me add to the point that everybody can understand key mathematical concepts and ideas if they are explained the right way. First, let's watch a video from young Sheldon.
He's failing math.
Some of us can relate to that.
Alright, I'm given to understand you have a test coming up on negative numbers and fractions.
Yeah.
So, what part don't you understand? Oh boy. Let's take it back a step. Where do you stand on addition, subtraction, multiplication, and division?
I'm against it. Oh boy.
Alright, let's talk about negative numbers.
I'm all ear.
Ears.
No, ear. This one's clogged.
So Billy isn't as stupid as one might think.
Right. Okay. Negative numbers are numbers that are less than 0.
But zero's nothing.
Yes.
So how can you have less than nothing?
Let's see. How about this? If you have $1, that's 1. If you have no dollars, that's 0. But if you owe me $1, that's -1. Does that make sense?
I think so.
Alright, we're making progress.
Mom! I owe Sheldon $1! I think I understand.
Good.
One question. How can you have 0 if 0 is nothing?
Without something that you have, 0 represents a state of nothingness.
What does that mean?
It's nothingness, the absence of somethingness. Trust me, 0 is a thing.
But you just said it's a nothing.
I did.
Which is it? A something or a nothing?
Here we see 2 points. One is that Billy is confused between something and nothing. The second is he doesn't move on to the next part. He stays stuck. Well, most of us accept that 0 is absence of something. For example, if I don't have any oranges, then I can say I have 0 oranges. I don't have any oranges is the same as saying I have 0 oranges. But it's so unusual because Just like I have 0 oranges, I can say I have 0 billion dollars. It feels so nonsensical. It serves no purpose except in maths and similar situations. So Billy doesn't want to accept it. He understands it, but the seemingly useless idea doesn't let his brain even assume that. Now this is just 0. Imagine a similar kind of horror one might have felt when they must have learned the definition of a point. In geometry, a point is an abstract idealization of an exact position without size as 0-dimensional objects. Imagine a similar kind of horror one might have felt when they must have learned the definition of a point. I mean, how can that point even exist if it is a 0 in all dimensions? But what they actually mean is a point is so small that we can practically say its dimensions are 0, and we can ignore that. Let's continue. The problem is, while the world at large is always talking about planets, atoms and DNA, chances are no one has ever talked to you about the fascinating ideas of modern math, such as symmetry groups, novel numerical systems in which 2 and 2 isn't always 4, and beautiful geometric shapes like Riemann surfaces. Let us see how they look like. Mind-boggling. It's like they keep showing you a little cat and telling you that this is what a tiger looks like. But actually the tiger is an entirely different animal. I'll show it to you in all of its splendor and you'll be able to appreciate its fearful symmetry. As William Blake eloquently said. Don't get me wrong, reading this book won't by itself make you a mathematician, nor am I advocating that everyone should become a mathematician. Think about it this way, learning a small number of chords will enable you to play quite a few songs on a guitar. It won't make you the world's best guitar player, but it will enrich your life. In this book, I will show you the chords of modern math, which have been hidden from you. And I promise that this will enrich your life. One of my teachers, the great Israel Gelfand, used to say, people think they don't understand math, but it's all about how you explain it to them. I agree. If you ask a drunkard what number is larger, 2/3 or 3/5, he won't be able to tell you. But if you rephrase the question, what is better, 2 bottles of vodka for 3 people or 3 bottles of vodka for 5 people? He will tell you right away, 2 bottles for 3 people, of course. I think someone can try this on a drunk person. My goal is to explain this stuff to you in terms that you will understand. I will also talk about my experience of growing up in the former Soviet Union, where mathematics became an outpost of freedom in the face of an oppressive regime. I was denied entrance to Moscow State University because of the discriminatory policies of the Soviet Union. The doors were slammed shut in front of me. I was an outcast, but I didn't give up. I would sneak into the university to attend lectures and seminars. I would read math books on my own, sometimes late at night, and in the end I was able to hack the system. They didn't let me in through the front door. I flew in through a window. When you are in love, who can stop you? 2 brilliant mathematicians took me under their wings and became my mentors. With their guidance, I started doing mathematical research. I was still a college student, but I was already pushing the boundaries of the unknown. This was the most exciting time of my life, and I did it even though I was sure that the discriminatory policies would never allow me to have a job as a mathematician in the Soviet Union. But there was a surprise in store. My first mathematical papers were smuggled abroad and became known, and I got invited to Harvard University as a visiting professor at age 21. Miraculously, at exactly the same time, perestroika in the Soviet Union lifted the Iron Curtain and citizens were allowed to travel abroad. So there I was, a Harvard professor without a PhD, hacking the system once again. I continued on my academic path, which led me to the research on the frontiers of the Langlands program and enabled me to participate in some of the major advances in this area during the last 20 years. In what follows, I will describe spectacular results obtained by brilliant scientists, as well as what happened behind the scenes. This book is also about love. Once I had a vision of a mathematician discovering the formula of love, and this became the premise of a film, Rights of Love and Math, which I will talk about later in the book. Whenever I show the film, someone always asks, does a formula of love really exist? My response, every formula we create is a formula of love. Mathematics is the source of timeless, profound knowledge which goes to the heart of all matter and unites us across cultures, continents, and centuries. My dream is that all of us will be able to see, appreciate, and marvel at the magic, beauty, and exquisite harmony of these ideas, formulas, and equations. For this will give so much more meaning to our love for this world and for each other. Guide for the reader. A guide for the reader. I have made every effort to present mathematical concepts in this book in the most elementary and intuitive way. However, I realize that some parts of the book are somewhat heavier on math, particularly some parts of chapters 8, 14, and 17. It is perfectly fine to skip those parts that look confusing or tedious at the first reading. This is very important. That is what I often do myself. I think it is important to simply proceed further when we don't understand something. I mean, like, what if what we read in the future helps us understand what you have read already? Coming back to those parts later, equipped with newly gained knowledge, you might find the material easier to follow. But that is usually not necessary in order to be able to follow what comes next. Okay. Some mathematical concepts in the book, especially in the later chapters, are not described in every detail. I can understand, I mean, like if it goes into too much detail, it might get out of our grasp. My focus is on the big picture and the logical connections between different concepts and different branches of math, not technical details. A more in-depth discussion is often relegated to the endnotes, which also contain references and suggestions for further reading. However, although endnotes may enhance your understanding, they may be safely skipped, at least at the first reading. I have tried to minimize the use of formulas, opting whenever possible for verbal explanations, but a few formulas do appear. I think that most of them are not that scary. In any case, feel free to skip them if so desired. A word of warning on mathematical terminology. While writing this book, I discovered to my surprise that certain terms that mathematicians use in a specific way actually mean something entirely different to non-mathematicians. Let me show you an example. For example, to a mathematician, so let's return to the example that the author has shown. For example, to a mathematician, the word correspondence means a relation between two kinds of objects, as in one-to-one correspondence, which is not the most common connotation. There are other terms like this, such as representation, composition, loop, manifold, and theory. Whenever I detected this issue, I included an explanation. Also, whenever possible, I changed obscure mathematical terms to terms with more transparent meaning. For example, I would write Langland's relation instead of Langland's correspondence. You might find it useful to consult the glossary and the index whenever there is a word that seems unclear. Please check out my website for updates and supporting materials, and send me an email to share your thoughts about the book. My email address can be found on the website. Your feedback will be much appreciated. In the next video, we'll start with chapter 1 and we'll read 3 to 4 pages a day, not more.